Welcome to section 4.3. All right, so we're going to continue talking about our bases, specifically the spanning sets that we actually used in the last section. We're going to talk a little bit more about how to write down the spanning sets in most simplified form. Because we mentioned before that there is a spanning set. So there's multiple spanning sets. But let's talk about what's the best spanning set to write down. So let's review and let's talk about bases and do a basis example. So first off, we need to talk about linear dependence. So a set of vectors is linearly independent if the only solution to this linear combination equaling the zero vector is if all the scalar coefficients are zero. Now, it's linear dependent if there's any non-zeros that are involved in this. So these are definitions that we already did. So remember, they're one or the other. A set of vectors that are linear independent or linearly dependent. So based on this, a dependence relation is a vector equation that satisfies this, as long as all the C's are not zero. So anything that's not, at least one of them has to be not zero. All right, now this applies to basis because a basis is a subspace of a vector space. And so if any subspace, in fact, the basis of that subspace is an index set of vectors. So a set of vectors, if it has two things, it's linearly independent and it spans. So it's a linearly independent spanning set. So we need two things to be true. We need to show, anytime we're showing that something is a basis, we have to show that it is linearly independent and that it spans. Okay, so we usually refer to things as the standard basis. Now the standard basis for Rn are the vectors E1, so forth. Now these are vectors that we've already talked about before. So E1 is the vector that's 1, 0, and it's just zeros the rest of the way. E2, on the other hand, is going to have 0, 1, and then zeros the rest of it down, and so forth. So En, or Ei, is we get an I, in the ith place, there's a 1, and there's zeros everywhere else. So these vectors are considered the standard basis. That doesn't mean they're the only basis, but they are the standard one, and they're the one that is used most often. And we like them because they're very, very simple. So we often try to write things in terms of similar matrices. Now, we do have an important theorem as we're going to talk about this basis concept known as the spanning theorem. Now, let me read you this and then let's interpret it. So we have a set of vectors, V1 through Vp, and we say that H is spanned by that set. If one of the vectors in S is a linear combination of the remaining vectors, then the set formed from S by removing Vk still spans H. So in other words, if one specific vector is a linear combination of the others, I can take it out and I still have it. And as long as H is not the zero set, some subset of my original spanning set is a basis. So every basis is a subset of a spanning set. Maybe the entire spanning set, and maybe only a portion. But we can leverage this as we get into our examples. So let's consider this. I have three vectors, V1, V2, and V3. And we say that H is spanned by them. Now quickly note that V3 is a linear combination of V1 and V2. Oh, no, that should be V2. I just saw that, sorry. That should be V2, my apologies. So if we know that, then we actually can say that the span of V2 is equal to the span of V1, V2. And now we need to find a basis for the subspace of H. Well, we already know that we can use V1 and V2 because they're a spanning set. We don't know if they're a basis. So are V1 and V2 linearly independent? The answer to that is yes, because they're two different vectors. And because V1 and V2 already span everything, because we've just shown that V1 and V2 is equal to the span of V1, V2, and V3, then we just look at V1 and V2, and because V1 and V2 are spanned by, so all of this is just to show that V1 and V2 still span the whole thing. So they're a potential basis as long as they're linearly independent. Now, they're linearly independent because they are two vectors, and two vectors are linearly independent as long as they're not scalar multiples of each other. Obviously not, because we have a 0 over here and a -1 over here. So clearly, you don't even need to do any calculations. We know that they are linearly independent. So this is actually this is a problem that you'll notice is less about computation and more about using your critical thinking skills, putting together the concepts that you already know. So we're just looking at these things going, what's the smallest set I can come up with that spans the whole thing? And I just need one of that size. All right. So this takes me to my second example, which is actually a little bit more tricky. Let's consider the basis for U3, which is 3 by 3 upper triangular matrices. And I'm going to show that there's 6 following triangles. Now, what this is, real quickly, let me do an example before I get into my primary basis. This is anything I can write as A, B, C, 0, D, E, 0, 0, F. So it's anything that can look like this, where A, B, C, D, E, F can all be different numbers. They can be anything in the world. They can be any real number. Now, the basis for this, I'm going to show in a second, is actually 6 matrices. And I'll show you what they look like. It's really interesting because this is one of the situations where my vector space is not vectors in the traditional sense of what many people think of vectors. The vectors are matrices. But I'm going to show you how you can look at them as traditional vectors. Now it gets a little bit more complex. So clearing this out, so we have space for me to show you I'm going to show you actually that these 6 matrices are the basis. And first off, you can notice that if I do A times this first one, and then B times the second one, C times the third one, D, E, and F, and add them all together, if I do this multiplication, then add them together, I get the matrix that I just wrote down a minute ago, which is why they represent all of them. Now we can, as I said right here, it's intuitive that you can come with these basis, these 6 matrices as a spanning set, but remember to show that they are linearly independent, that's going to be a little bit tricky because the strategy we've used to date to show that a set is linearly independent is to turn it into a matrix and then row reduce it and show that I have that many pivots. So how do I do it in this particular case? Because I can't have a matrix of matrices. Well, there's actually a cute little trick. So as I just mentioned before, we usually turn them into vectors. Well, we usually turn the vectors into columns in a matrix, and then we just make sure the null space of that matrix is just the 0 vector, which means it has the number of pivots. Again, we have all those different theorems that we get to leverage. We can't have a matrix of matrices. So we're going to trick ourselves by using vectors, an m by 6 matrix. Here's what it is. This vector actually corresponds with the matrix 1, 0, 0, 0, 0, 0, 0, 0, 0. This one corresponds with the same thing, just change it to be 0, 1, 0 in the first row, and then zeros everywhere else, and so forth and so on. Well, real quickly, just looking at this matrix that we have right here, it's not that hard to quickly notice that it has how many pivots and how many free variables. Well, it has 6 pivots and no free variables, which means that its null space is only the 0 vector, and that those columns are all linearly independent. Those columns represent the matrices we already did, and for that reason, we can leverage. Now, why this works is actually using linear transformation that is 1 to 1 and on to. But I won't get into the details of that. There's a reason that I was able to do this. But can we think about a different way to do this? There's actually another way you can do this, and that is by turning into a 6x6 matrix. Can you think of what that would be? That's just a fun little thought process to leave you with. Again, if you have any questions, let me know. Otherwise, good luck, and I hope you do well.